Yeah, once you start talking, I'll turn it up a little bit because I couldn't hear you earlier.
Okay. Do you want me to start and then you'll calibrate from that?
So I was like, I had to like get off the phone as fast as I could. I had to check my email.
Is this good?
Yeah.
Okay, everyone, I think we're ready to get started. Welcome to our October meeting. And just to reiterate, we have Wi-Fi if you need it, connect now, our jobs board, and our Slack is written up there. So this talk is about explainability of models and Shapley values. We have Thomas Stearns from DataRobot giving this. Please join me in welcoming Thomas.
Set up here. Can you guys hear me? Is this good? This is not a big space. So. Oops. So, Sarah, thanks for the really warm welcome, and thank you guys for lending your after-work evening. That's not always easy to do. So tonight I'm going to talk a little bit about model explainability and one of the more in vogue ways of approaching a problem like that called Shapley values, which is currently an open source package that you can use on some of your favorite models. So I should put a little bit of an agenda together. Very brief introduction, just what I do, who I am. We'll talk about Shapley values and why you should actually care about them, why I think it's probably going to be more and more important as the data science revolution goes on here. We're going to talk about using Shapley values for prediction explanations, in particular, in a predictive modeling situation. And I hate to give a technical talk and not make your lives, if not easier, then a little bit more interesting. So we're going to talk about some practical applications of Shapley values. And of course, we'll do questions, and you can argue with me if you want at the end of it. So, okay, so just to hear my life story. I'm currently a data scientist at DataRobot, which is right over there, just right up the street, a couple buildings down from here. DataRobot is a software company, and our flagship product is a machine learning platform, where essentially you can upload your data as a customer, and the software takes a look at some of the heuristics of the data and the properties of it, and basically make some educated guesses about what sorts of models are going to be successful on the supervised learning problem that you've specified. And you are then able to, using the platform, examine those models, look at their properties, how well they do, and eventually deploy them in an end use case in our cloud or on premises. I don't want to plug for DataRobot too much. And the other theme that's going to come up here tonight is a lot of I should talk about the group first. I'm in a group called Explainable AI in DataRobot, and it's not exactly our charter, but part of what we're interested in. We've all heard tropes about how do you figure out what's going on with some of these black box models, they're too complex, how exactly do you explain the results to customers, and tropes like that, and we want to kind of push back against those and say, well, you can do it if you're careful about it and care about the results being really, really good. And the other issue is that a lot of the customers that our group interfaces with are in regulated industries like insurance and banking, and that's going to be a theme of some of the talk. So let's talk about Shapley values. It's kind of a romantic, I think, origin story where you have this mid-20th century idea that actually comes back to life like 70 years later. So I wanted to talk a little bit about like classical Shapley values. They were invented by an economist named Lloyd Shapley, I think in 1955, maybe. And he was a game theorist, and he was interested in a question that had come up. Game theory is much, much younger than it is now. He wanted to tackle the question, if you have a team that is contributing to some outcome and that produces a payoff for those teammates, how do you split it equitably when the players have different abilities or contribute different amounts or issues like that. And I don't want to use, when you talk about teams and stuff like that, you have to kind of go to the sports metaphor, unfortunately. If you can imagine you have a soccer team which has maybe a strong defensive player, a weaker defensive player, and a goalie, and you're trying to see how much of the team's victory or loss could be attributable to each of the players, you want to see, you might think that the best way to do it is kind of run the game with and without the players. But it gets a little bit more complicated than that, because if you withhold the strong player from the game, the goalie's value is going to go up if you win, right? Because he's had to do more in the absence of the strong player versus the weaker player. And that's kind of the rough way to think about it, is that you're adding and subtracting players, but they are affecting each other's contributions in strange ways. So Shapley's main insight in the formula that he produced, you can assume things A, B, C, and D, and the formula, in a real sense, is the right answer to the question. That you can prove that if there's some other payoff function that satisfies the properties that we're assuming, those are the Shapley values. There's only one answer. So it's really, really nice kind of theoretical formal result, which at the time had no practical implications essentially at all. I think he won the Nobel Prize for something entirely different. It kind of was a cool result, but not super interesting for business people or anything like that. Okay, so I'm going to go through the math very, very quickly here. You're trying to calculate the Shapley value for your ith player here. And the way that you essentially do that is the withholding strategy that I brought up in the soccer example, where you have, I have a laser pointer here, I'm going to tell you. You have the ith player being withheld on some subset of the players, S. And the subset in the soccer example that I gave would have been the 3 players, the strong defenseman, the weaker defenseman, and the goalie. So you want to see what's happening on that subset of players when you withhold one of the players from the game. And you want to kind of do that over all of the subsets, which is where this sum is taking place over. You're looking at all of the subsets withholding the ith player, and then you figure, well, all of the subsets are not the same, right? You want to kind of weight them by the number of such subsets, right? And in this way, this formula is the way that Shapley values are classically formulated. Are there any questions about this?
So when you say number of subsets, do you mean, is it like a recursive thing? So
Sorry?
maybe you could have a subset with one player, a subset with 2 players. Is it like that?
Or it's a
just take
it's,
away one?
it's all of the possible subsets. So like the power set, you could have 3 players, 4 players, however many players that belong on the team. But it's all of them on different, you're partitioning in it, right? Does that make sense? It's the power set. So if there's n players on the team, there's going to be 2 to the n of these different subsets. So that brings this a little bit of a full circle. That's a timely question here. You might have noticed that sum has exponentially many terms and the number of players. Lots of real-world applications have lots of players. We're not talking about 2 players, or even like a soccer game's worth of examples, or a soccer game example where you have, I don't know how many players are on a soccer team actually. 11. Okay. 11 you might be able to kind of brute force, but more than that, if you're talking about an economy, obviously that's not feasible. And perhaps even more important, as your parents said, life is not a game, right? How exactly would you withhold a player from a soccer team and then just run the game and observe what's going to happen, not just withholding each individual player, but withholding each individual player with all of the particular subsets of players. This is just, life doesn't really work that way. And that's why this was kind of a theoretical result that got some attention, but ultimately was not super interesting to lots of people. So somebody noticed, I actually don't have a reference for who originally thought about this. Well, is soccer really that different than predictive modeling? You have a modeling task which has an outcome. The model makes a prediction. You're trying to make the best prediction you can. The features are making up a team that contribute to the model in differential ways. We all know that not all features are created equal. Some of them are good, some of them are bad. And the modeling output you can measure will make up the team's performance. And also, like this addresses the previous issue, in modeling, you can actually marginalize over a player's performance, or over a feature's performance, which is not what you can do in a soccer game. There are ways of, doing the marginalization correctly. So this suddenly became more interesting, and this is kind of the big explainability question as far as I'm concerned, as a result, if you're interested in prediction explanations. So you have a single row, and you want to attribute the model's prediction for that row across all of the features, right? So this is a local type of feature importance, not global. You're interested in just a single row. And there are a bunch of Shapley values that I just made up on the top here, and a bunch of features that will make up the model on the bottom. And the way to think about this is that the features with positive Shapley values are pushing the prediction this way, and the negative ones are pushing it the other way, and they kind of arrive on the prediction that you have here. And then you have, because you have training data, you also have a baseline model prediction, which you can just define as like the average of all of the predictions on the training data, for example, which is kind of the exemplar prediction. And I mentioned before the magical additivity of the Shapley values, but you get this result that the difference between those is actually the sum of all of the Shapley values. So the Shapley values add up to the prediction's deviance from your exemplar prediction. Does this graphic make sense? I didn't spend a lot of time on it.
So the exemplar, is it so all your rows basically you kind of average predictions?
Yeah, you're saying how is the difference between my row, that deviance accounted for in all of the features? And this difference is what all of these numbers add up to. So the Shapley values in some sense add up to the prediction. Are there any questions about this?
So if it's a negative Shapley value, does that mean that the effect of that particular feature is also negative on that prediction?
Yes, that's what it means. That's exactly what it means. So you can imagine that if you have some distribution of predictions, as you get to one end or other of the tails, this force plot starts getting more and more red or more and more blue, because the values get more and more extreme, and there's only one way for the prediction to get to such an extreme value, and that's if all of the features are working in one direction. Okay, just some technical points here. This is no different than the classical Shapley values. You still have an exponential number of terms to calculate them exactly, and as a result, this is seldom possible to do. Somebody said that you have 11 players on a soccer team. You could probably do that on a small feature set like that and just brute force it. Any more than that, these modern machine learning models have like hundreds, dozens of features. It becomes much, much more computationally complex. And there's this other result where if you have a linear model, you can calculate exact Shapley values because the Shapley values are actually just a linear transformation of the model's coefficients, which makes some intuitive sense that you would want models with higher coefficients to get larger Shapley values in importance. So due to this complexity, there was this pretty substantial literature over the past like 50 years that figured out ways to approximate these values. There's even modern ones too for some of these deep neural networks. I think Deep Explainer was one where you can actually get this cool heat map on an input image, which points at the pixels that the model finds interesting. Not exact Shapley values, but it's still a really interesting use case. And the other way of doing it is basically Monte Carlo simulation, where you go through and sample from the distribution and get an approximation for what happens when you add and subtract the features together. Okay, so for the actual applications, the talk is titled Model and Explainability. You want to be able to do feature engineering and examine what's happening locally with the model. It's another way of kind of interrogating how it was trained and how it's making the predictions. That's what my group does. The other one, we're at Mass Mutual here, you have to be able to justify the predictions that the model makes if it's actually making business decisions. So if the person comes in and wants some credit and the model says that they're too risky, well, you can say this is how your shortfall is distributed among the features in the model. And because you have this magic additivity, everything kind of adds up, and it becomes like a very compelling user experience. Feature importance, I've mentioned this briefly. All of these explanations are at the row level, so it's all local importance. You can do basically just mean aggregation over the explanations and get a measure of global importance for all of the features in the data set. And we've shown that we've probably mostly, all of us have heard of like permutation-based importance. Some of the testing that we've done shows that this type of global feature importance has some more desirable properties than. The other one that I don't know how mainstream this is, but it's something called supervised clustering. Most clustering that we do is unsupervised, and we'll talk. Has anyone heard? Oopsies. Has anyone heard of this or used it before? No. Cool. We'll talk about it then. So the story goes on here. Last year, a researcher named Scott Lundberg wrote a paper which showed how to calculate exact Shapley values in decision tree-based models. And as you can imagine, it was a pretty exciting development. No one had been really interested in this that much. Oh no. Okay, sorry about that. Yeah, no one had been that interested in this until this paper. And this has, I mean, everyone in this room has probably used decision trees at some point in time. You can have exact Shapley values, which have these magic properties for those models. And suddenly this got more fashionable. And I just Googled trend, like SHAP values and Shapley values over the past couple of years. And I don't know, it doesn't really prove anything, but it's cool to look at. And this is fashionable now. So along with the paper, Lundberg published an open source library that it's called SHAP. It basically goes in and examines the tree structure for all of our favorite decision tree libraries. XGBoost, LightGBM, and scikit-learn in particular. Not all of scikit-learn, but enough of it. It parses the tree structure and will actually, you can set up an explainer on the model that you've trained and recover the Shapley explanations from them. Okay, so I promised I'd talk a little bit more about some applications so that I make your lives more interesting or enrich them, hopefully. So this is not the only way to do this, prediction explanations. I was chatting with Sarah that you guys had used Lime internally for prediction explanations. This has some downsides. For one thing, basically the idea behind Lime is you take this model surface and you do some simulations and try to get a local linear approximation for what the model is doing, and then look at the coefficients of those surrogate linear models, and you can get a local approximation of what the model is doing at that point. This has some downsides. For example, if you have a tree-based model where the output is a step function, how exactly are you supposed to approximate linearly a step function right around the discontinuities? Like, you can't, right? So the authors actually know this. So I think they've published on it, but I promise to not plug too much for DataRobot. We have an internal method that we've designed called XEMP, which I think is exemplar. I don't remember what it is. I'm not going to talk about it too much. So like I said, we have the magical Shapley additivity. We found that, or I don't know, the word on the street is that the additivity is really useful for like C-suite people. They really like that it adds up to exactly what the prediction deviance actually is. And business people also really like it. It's extremely intuitive. For all of these other ones, you're just going to get like a bunch of numbers, right? So you can rank order the numbers and see what the method thinks are the more or less important features in the prediction explanation, but it's not, it doesn't have the magical SHaP properties. It's deterministic. I mentioned before that line relies on some of these sampling procedures and simulations. Tree SHaP will work the same exact way every single time. So the only randomness is in how the model is actually trained. That obviously will change things model to model, but once the model is fit, the SHaP values are identical using the tree SHaP explainer. Okay, so the bad stuff, it's not model agnostic. If you want to use if you want to use fancy neural networks, you can use Deep Explainer, but you're not going to get the exact values, and that's kind of a problem in a lot of circumstances. And like I said, most of our customers are in regulated industries where the work that you do has to be justifiable, if not to a regulator, then into like an internal model validation team. And it's one of these situations where like the bureaucratic people are interested in the most open source scientific approach of doing something, which doesn't always happen. But in this case, this is in fact what they want. They want something open source. They don't want an kind of proprietary in-house method of doing prediction explanations. And because you can calculate the exact value every single time, it's really attractive to teams like that who have to justify what they're doing to higher ups. Okay, so in addition to the prediction explanations, I wanted to talk a little bit about supervised clustering, which I'm glad nobody's heard of. So once the model is trained, you can actually cluster on or do dimensionality reduction on the explanations instead of on the training data. If you think about it, the training data has the same exact size as the explanations. You're getting, for each feature and each row, you're getting an explanation. So those are the same size, and you can do clustering on the explanations themselves. And it asks a slightly different question. It's like, what structure does the model see in the data instead of what the training data actually looks like? And anyone who's ever done k-means or k-medoid clustering knows that it's quite a fine touch to get it to work. You have to scale everything correctly, and it's a hassle to do. Doing this and using the Shapley values, because you have the additive properties, all of the features have the same additive unit. Because they all have to sum up to the same thing. So it's an interesting way of scaling the data in a way that is using the model's information. And I'll give an example of this. This is essentially a plot using the two different things. I took our favorite data set here, and the supervised clustering uses a very vanilla XGBoost classifier. And the plot on the left is just dimensionality reduction down to 2 dimensions on the pre-processed data. So not super interesting. Kind of looks like Greenland. On the right, this is not dispositive that there's structure in the data, but you can see that the effect is significantly different, that you're not getting the same exact thing. And plausibly there are clusters, although it could be noise in this case. I'm not saying that it proves anything, but the effect is significantly different using the exact same method of dimensionality reduction in both cases. Okay. I'm all done. You guys have questions, or we can argue now?
So,
Yeah. No, go ahead.
So, okay, how is doing clustering on the Shapley values different from, say, doing a logistic regression on them? Because I'm going to get coefficients, and it's not exactly like unsupervised to do clustering, right?
I don't exactly follow the question. I think if you do you're talking about doing a logistic regression
On the Shapley values. rather than do it?
There's no reason that you couldn't do that. Yes, you could. I mean, how would you get the positive and negative classes?
We have, so it's already a supervised tree.
Oh, I see what you're saying. Yes. Okay. I guess you already have the supervised component. You could do that. I've never heard of anybody doing that. I was just giving one use case. Is that the Shapley explanations give you this entire transformed data frame that takes the model's perception of the data into account, that you can do interesting things with. Yes.
So let's say you take the Shapley values and aggregate to the mean. Are those, so when I'm, building a model and testing it out, there's always in the library a, dot feature importance.
Yep.
Is that, this could just be my not knowing the depth of this stuff. Is it a similar concept? I mean, is it sort of saying a similar thing?
So I think the dot feature importance, like for example in scikit-learn,
Yeah.
I think uses either tree-based importance if it's a tree-based model, or it uses permutation importance. I can't remember which one.
Yeah.
Those are measures of kind of global importance, and I think.
Right. So I'm just saying, like, if I were to get the mean of a feature over the
Yeah. So you get positive and negative Shapley values.
Oh.
You would do mean absolute aggregation.
Yeah.
So you take the absolute value and then collapse it by averaging, and you would get a measure of global importance. Yes, that's correct.
So that's kind of I just like kind of a similar output would be Shapley in that.
It would have the same exact shape. Yes, that's right.
Okay.
One value for each feature. Yes, that's right. Nishant, how's it going? Yes.
Okay, so you mentioned in between that the Shapley values are sort of some transformation of the coefficient parameters. So is there an equation that you can use, like a generic equation that you can use for transforming that for any kind of parameter?
Yeah. Is there a marker? I can really write it down if you want me to.
To the far corner.
And another one maybe after that is if you can also explain the global and local feature importance that you're talking about.
So the Shapley value for this row here would be the coefficient of the model times the deviance from the mean over the data. Is what the Shapley value would be for the linear model. What was sorry, I missed the second question.
Yeah. So what's the difference between the global feature importance and local?
Yeah, so the difference between the global and local feature importance is that you can, with Shapley values, you can examine what the model thinks is driving a single row's prediction.
So if I were to understand this from an example, so I'm talking about a customer.
Yes.
And so for this customer, which of the features are making him purchase whatever he's purchasing, and for some other customer it could be something else.
That's exactly right. Yeah, it's at the row. Assuming that the model is trained at the customer level, yes, that's exactly what you're describing.
So sorry.
I'm just going to add on to that. So let's say you have a row, it spits out a prediction. You're like, I don't get why it's doing it that way.
Yep.
You could use it this way, like, oh, if I look at the Shapley values, like, oh, clearly because blah blah blah. Using Shapley could help you figure that out.
I don't know how clear it is, but yes, you could do that. Yeah, that's right. Yes.
When you're aggregating the local feature, when you're aggregating the local feature importances to get a global feature importance, is there a theoretical reason that you want to use absolute values rather than say squares and then take the square root or something like that?
Squares are nice, but no, there's no theoretical reason. I don't think. This isn't one of the situations where like the squares behave better or anything like that.
Right.
I don't think. That's just the way that.
But it's also not a situation where the absolute values necessarily.
There's no theoretical justification. We're just making it up as we go along here. So,
So if I understand this correctly, you should be able to probe the Shapley values to get an idea, get an understanding of bias in the data, or in the model rather, right? So if you looking at a certain subset of your rows, and they all have a certain Shapley value.
Yeah.
Just to put it in very blunt social terms, if you have people of color with a certain trend in Shapley value and white people with the opposite one, then that would show extreme bias, right?
You could do the sort of disparate impact analysis that you're talking about. Yes, there's no reason that you couldn't. You could observe how different features in the model were affecting different subpopulations differently. There was a lot of difference in that, but you see what I'm saying? Yeah, you could subset the Shapley explanations by population and study how the explanations differed between those two populations. Yes.
Just a quick question: do you see people that use your platform doing that type of bias analysis using Shapley or other things?
Personally, I think it's all science fiction at this point in time. Yeah, you can define bias like a bunch of different ways that don't have that are kind of exclude each other. So we all know about statistical bias and what that means, but I don't think that's the question he was asking.
I mean, a model being talking a protected class, or looking at demographic data and how you can see bias based off of that, or something like that. Maybe bias is the wrong word.
Yeah, but I think bias is the wrong word. I think disparate impact might be better, but you could do that. Yeah. I don't know if people who are doing it super duper well. Yeah. I mean, it's a very tough question, and obviously a controversial one. Yes.
I'm interested in doing a thought exercise, thinking about legislators, regulators that might look at certain ways of explaining models, and seeing the features of Shapley values, that they're additive, and have a tight fit between baseline prediction and where things actually end up with your model. I'm wondering, just totally speculatively, what you think might happen if people start seeing that in the public sphere a lot. Would regulators start thinking away and they might legislate around that? What do you think might happen just as this catches on?
Well, that doesn't sound super good to me, but from a DataRobot perspective, that would probably be okay. I think that is possible. Not everyone has access to the same models or data or anything like that. So there's that issue. But yes, open sourcing something like this could have a theoretical effect like that. I could see that happening.
Looks like we have started to. Oh, sorry.
So, Shapley values here are for tree-based models, right? So suppose in unsupervised clustering, I've built a bunch of clusters with my data, and I want to know why each of the data points are falling into a particular cluster. Is there something similar to this which can be applied there, so that I know what features are making something fall into a cluster?
Sure. I can imagine a workflow where you would train a new model that took the data and predicted which cluster it would fall into, and you could run an explainer on that. Does that make sense? You would get a new classification model, and the results of the SHAP explainer would show why the features fell into each of the clusters that you had already predetermined. But I think you would need, in order to do that, you would already need oh no, I guess you wouldn't need a label to do it. No, you're right.
Okay.
You could do it that way. Yeah.
Okay. Your previous slide had an image. Oh, awesome. Sorry.
This one?
There was a slide that had Greenland on it.
Oh, yeah.
By Greenland, I mean Japanese data. Yeah, that one. So you can still see the two distinct clusters on the left on both of them. Do you know what that is, or what the?
I basically wanted to just illustrate the differences in clustering outcomes that could happen by doing this. I didn't put a ton of analytical effort into it.
I'm so glad something you put extensively with.
No, this was my first time doing this, so I just wanted to see the difference, and it turned out good for a talk like this. So
yeah. So we still have some time that we can keep talking. Sarah, did you want to say a little bit about your stuff? I'm just curious for formats. We're experimenting with, this Q&A format. If you guys have any ideas on how to do what's called open spaces or like other discussions, we like our speaker/person back and forth conversations, but I'd also love to get more like basically get him to stop talking and you guys. So if you have ideas on how to do that, let me know. I'm going to start with one by having Sarah talk.
Yeah, I'll try to get away from the speaker so I don't pass it back. So who here has to like focus on explainability of their models for various reasons, whether it be regulations or just the nature of what you're modeling? So a couple of people.
raise your hand up, raise them high.
Yeah. Okay, so I'm seeing, myself included, about 8, 7, 8, something like that. Which is, a little less than I was expecting.
I was expecting it to be twice that. Okay.
Yeah. So one of our main models is used to predict someone's risk class for life insurance applications, and it's very important that our model outputs why we're giving them the risk class that they do, and we hear about it if it's not what makes sense to them, if it's not what makes sense to the medical reviewers who get those complaints. We decouple our modeling with the explainability. So we used to use Lime, now we're using Shapley values, and when we switched to that, we've had a lot fewer complaints about what the model's doing, which is really awesome. I don't have a hard number to go on that, but the medical team told us that they've been getting fewer complaints. So it's more intuitive, it seems, in the outcomes. Does anyone have an application that they think that Shapley values could be useful for that you're not currently using? Yeah.
So one project I worked on is about how to explain the reason why we see people redeem from mutual fund. So we have a market campaign. So one thing is we have to predict who are likely to redeem like 3 times more than they have in the past 3 months and greater than $50,000. So then we can contact the people. So we have like one contact method is face-to-face meeting, and we have to provide some reason why these people showing on the list. So the salespeople have some talking point, and we provide Shapley value and pick the top 3 driver that we predict cause the large redemption, we think. And then the salespeople can look at these top 3 variables and make something up so they can start a conversation. So I think it's a great application of using Shapley value. I have done this at the beginning of this year.
Yeah, that seems really interesting.
Yeah.
There's actually like customer facing.
Yeah.
I can talk about similar examples because I also my client is also a fund management company, but this is something that we're thinking about doing. We've not done it yet, and we've been exploring similar things. So we have been looking at we are wanting to work on an explainer system, which is kind of what we've just learned. So the situation is that we have developed a scoring algorithm for prospect customers for the fund management company, and the scores go to the contact center team. Now, they don't know why one person is scored higher than the other. So they come back to us as the development team that, I have worked with this X person and I know who or how this person has dealt in the past. The other person I don't know, this is probably new to me, new assigned to me, and I don't see why this person should be scored high. So then our thought is that when we are able to give them the explanation as to, because let's say this person has had high number of inbound or outbound calls, you've sent them more emails or they have responded to the emails, or they've had a good amount of AUM in the past, which is all these are features that go into the model. So now, if I have an explainer system, like with the way we call it, there I assume there will be less questions for us to be able to go back and look into the data. Okay, what was the specific case? What were the driving factors for this person or this client? So basically, they have the answer with them, and we don't have to look back at the data and find out for everybody that they want to question.
So my work was very similar to what they just spoke about. I was working for a consultancy earlier this year, and one of our clients was a bank, and they were selling multiple products like a lot of personal loans and insurances. So we built a lot of propensity models for those use cases, and we built XGBoost or Logistic, whatever worked. And apart from the scores, which is basically the propensity to buy a particular product, we also, to help the relationship managers who are finally the ones who are going to sell that product during campaigns or whatever, we had to, also let those relationship managers know why is that person going to buy the product in the future. So if I, want to sell a personal loan, maybe it could be a particular demographics or the spending patterns have kind of died down over the last few months. So those are the reasons why this person has a high score and would probably want to buy a personal loan. And also for customer churn, why would a person leave the bank? Why would someone close an account? So for all these different use cases, SHapley values really helped identify for each person what features were important in defining them as churners or not. And it also helped boost, it helped retain people or sell that particular product.
Any questions? Anything you want to argue about? I like your calls for arguments.
I hope it wasn't too controversial.
Wasn't controversial enough.
Okay.
I thought about arguing you about DataRobot, but I realized it would just give you too much of an opportunity to pitch DataRobot.
You gotta keep that. You gotta keep that crap out of it.
This is just a curiosity. Would it be possible to use this as like in the feature selection process? Like, would Shapley values be helpful there?
Yeah, we're doing a lot of work in that area. You're talking about using the global feature importance to kind of winnow down bad features.
Yeah.
Yeah, there's no reason that you can't do it for that. I guess we haven't found that it works much better on average than traditional permutation-based importance, but you can absolutely do it that way. Yeah. Yes.
I'll hand it to Matt.
It seems that how is this different than using PCA for feature importance? It seems like PCA will determine which features are most important, but then this will figure out which data points within that features are most important. Is that true?
Well, the issue I think is that the principal components don't have names, right? That you can point to. Whereas if you do explanations, you are getting for each of the features that are in the model, you will get an answer. Whereas if you just say, oh, the explanation for principal component 1 is this, nobody really knows what principal component 1 is, or any of the principal components. Does that answer the question?
Maybe.
Maybe. Yeah, ask it. Try again.
Well, if I've got, I now know which features are most important.
Yeah.
Now, if I just isolate things and look within that features, see a plot or whatever, does this then rank which features might be I mean, which data points within that set of features is most important versus least important?
Yeah, that's
Is that what we're doing?
That's a really interesting question. You can, so if you have imagine like a bell curve of predictions, right? You could look at which features are driving the most extreme predictions, right? And I think that wouldn't be a global measure of what you're talking about, but yeah, you could look at the extremes and see how the model is actually treating those on a case-by-case basis. I think I hope that answered your question.
Okay, I'll have to look at this further. Thank you.
Okay.
I want to ask this as a very open question to everybody, and the question might be partly because of my ignorance, but I'm interested to learn more about feature engineering in terms of how you generally go ahead and do that. In the sense that, so for linear regression, for example, I know I can see the parameter estimates and start from there. For random forest, I can see the global importance, but generic approach, what you tend to follow for your data science projects, like what are your top things or top priorities in doing feature selection?
Could help, I guess.
So first, this is what I do, but it's very subjective. I guess you can start off with looking at the distribution of the different variables and looking at the target variable also, and then seeing if there is not that much variation between the target and the variable itself, then probably it's not going to be important in differentiating. That is the first step, and then maybe if I want to even more than that, reduce how many features I'm considering for my model, maybe build decision trees and see where the variable is probably getting cut, so that it's pretty uniform throughout, and then again I see for the different bins of the features whether there is any variation in the target variable. And then also, if it's a linear model, maybe correlation with the target.
Right. So, but how does the complexity change if you have a lot of categorical variables too?
So, I guess we have to bucket them in some way. You can check the numbers, like how many data points you have for each of them, and also binning them in the right way. Again, it has to kind of make it, it has to also lead to the different bins having that variation in the target variable. Otherwise, it's not going to be important for the model.
Any other questions? Okay, great. Oh, yeah.
If I wrote a survey and then send it to you via Slack or a Bitly link, would you fill it in? Sure. Cool. I'll do that. We'll see if anybody fills it.
Great. Thank you all for coming out. Let's again thank Thomas for the great talk. We are skipping November and December, and we'll be resuming our monthly meetups in the new year. So, yeah, have a wonderful Halloween and holidays.
Yeah.